Hello everyone, welcome to this presentation called Simple-shear-flow for a Newtonian fluid. My name is Hugo, and in this video I will be using this audiovisual tool to solve one of the easiest and simplest flows from which an analytical solution can be obtained from solving the Navier-Stokes equations. So I will start by explaining this flow, why is it important. So we are going to use a Cartesian coordinate system. So we have x direction here, we have the y direction here, and z direction. So here I have a sketch of the geometry of a simple-shear-flow. So we have a fluid contained between two parallel plates. So these two plates are separated by a distance h, and the bottom plate is fixed. That means that it will not move. However, the top plate is going to move with a velocity uv. And in simple-shear-flow is the flow induced by a force in a fluid. So this sketch here is actually a 2D representation of the geometry, but the actual geometry will look something like this. I mean, in 3D we have this sketch, this small drawing. So we will be applying a force over here at this surface, and the force that we will be applying is going to take this form. So you probably recognize this equation from my previous videos. So this equation is the flux of momentum is going to be, this is the flux of momentum, is going to be equal to the product between the viscosity of the fluid multiplied by the gradient of the velocity. So here this index y means that the normal orientation vector, which is going to point out in this direction here. So we will be applying this force over this surface at the top, which is going to cause that the fluid, the top plate is going to move with a velocity uv, and this is going to cause a movement of the fluid in x direction. So that's why the index x is expressed here. So let me rewrite this. So here I'm representing some layers of fluids. That's what I draw these lines. So the layers of fluids that are close to the top plate are going to move with a velocity uv because they are very close in contact with the top walls. However, the layers of fluids that are close to the bottom plate are not going to move, or they are going to move with a low velocity value, and this is because the bottom plate is fixed. So in simple-shear-flow, fluid will move due to the velocity of the top plate. So as I said before, we are applying a force over this surface. So this is going to cause a movement of the fluid in x direction. So the upper layers of fluids will drag down the lower layers of fluid, the ones that are here. So we say that the momentum, which is defined as this quantity P, is equal to the product of the density of the fluid multiplied by the fluid velocity. So x direction is called the direction of propagation of momentum or propagation of movement. So in simple-shear-flow, we are going to propagate the momentum, the movement, from top to bottom. So momentum will propagate perpendicularly from top to bottom layer. So you remember the diffusion equations in mass, heat, and momentum equations, Newton's law of viscosity. We have Fourier's law, and we have fixed law of mass. So this kind of equations tell us that these quantities always are going to be transferred from higher concentration values to lower concentration values. So at the top plate we have a high concentration of momentum because we have a higher value velocity at the top. So this momentum is going to transfer from the top to the bottom. And as you can notice, the layers of fluids that are close to the top wall are going to have higher values of velocity compared to the lower layers. And this is due to viscous effects. And that means that the lower layers of fluids that are around here will move at a lower speed. And this is because there are energy losses. So our goal in this video is to find an analytical solution for the velocity field in this kind of geometries. So these kind of flows are important because they are really easy to reproduce in a laboratory. Therefore, the data obtained from these experiments are reported in the literature. You can find plenty of information for this kind of flows. Also, plenty of industrial processes of high importance, for instance, extrusion and polymeric flows, approximate to steady simple shear flow. So, understanding what is the physics behind these flows is important. And this kind of flows also will give us some information about the behavior of the materials, complex materials, and this kind of flows will also will be helpful to obtain the values of physical properties of different fluids, for instance, the viscosity and many other things. So let's make some assumptions or some points to consider in order to obtain the velocity field we are interested in calculating. So we will assume that we have an incompressible Newtonian liquid. So that means that the density of the fluid will not change, or it will not depend on the position, and it will not depend on time. Also, the viscosity is going to be, the density is going to be constant. We also assume laminar and isothermic flow. So I want to introduce this concept very quickly. Laminar. Isothermical flow just means that the temperature is going to be constant for the flow. So we will not introduce any sort of source of energy into the system. So laminar flow. So what is a laminar flow? So in laminar flow, the fluid elements will move in parallel layers without mixing. So that means that the layers of fluids move smoothly over one another, and the fluid elements move along uniform and predictable paths. So this type of flow is common where the fluid moves at low speed and where we have channels of a small size. So we will assume that we have small, or the values of H are very small, and also we will assume very low velocity values. So that means that B is also going to be slow. So another thing I want to mention is that we have, on one hand, we have laminar flow, but we might also, there is another physical phenomenon called turbulent flow, which is the opposite of laminar flow. In turbulent flow, we have a chaotic and unpredictable behavior of the movement of the fluid. So there is actually a very interesting experiment that was carried out by Reynolds in 1883. So he did some very interesting experiments. So he had some, I'm going to very quickly draw the experiment, so just give me a second. So this is 2, this is 1, and this is 3. So Reynolds introduced a dye, a colorant. So he had a fluid moving from this direction towards x direction. So he introduced a very small layer of dye colorant into the flow. So this is zone 1. In zone 1, he had this is a very controlled experiment. So he somehow managed to control the velocity of the fluid. So in zone 1, we have low velocity values. So the colorant, he observed, as I said before, the fluid is moving in x direction. So he introduced the colorant through here. So he noticed that the layer of fluid with the colorant remained the same. So the layers of fluid did not mix. So he had something very uniform. And then in zone 2, the fluid entered through zone 2, and then he increased the velocity values. And he noticed that now the colorant started to dissipate a bit, but it was still order. So it was a bit destabilizing, but the colorant could still be seen through the main layer of fluid. And at zone 3, he increased the velocity a lot. So he observed that the colorant dissipate through the channel. So he started to notice that the flow was no longer stable. It was very chaotic. And then we no longer had laminar flow. So he used this experiment to show that we might have 3 different states of flow. In zone 1, which is the flow where we had low velocity values, so he called it laminar flow, which is in zone 1. In zone 2, he called it the transition state, and in zone 3, he called it turbulent flow. So transition is basically the state of flow in which we go from laminar to turbulent flow. So he also proposed one of the most important dimensionless numbers used in probably physics and in fluid mechanics. So he defined, in order to determine whether we are in laminar or in turbulent flow, he proposed this dimensionless number, which is the ratio between these properties of the system. So we have the fluid density, so we have a characteristic velocity of the system and a characteristic height of the system or length divided over the viscosity of the fluid. So you can obtain the units of each of these quantities, and you will notice that this group, this ratio, will not have dimensions. So basically this number, which is called the Reynolds number, compares the inertial effects in the flow with the viscous effects. So if the Reynolds number is slow, so that means if Reynolds number is equal to 0, the viscous effects dominate. So that means that either the viscosity is really huge, or the velocity or the characteristic length or the density of the fluid are very low. So this is going to cause low values of Reynolds numbers. So when we have almost 0 values of Reynolds number, we have a laminar flow. However, on the other hand, if either the fluid viscosity is small, or we have very large values of velocity, or very large channels, or very large values of density, we have large Reynolds number. which means we have a turbulent flow, chaotic flow. So I just wanted to introduce this concept quickly because here we are going to consider laminar flow. That means that we will have low values of velocity, low values of the height of the channel, and also probably large values of viscosity. So this combined give us low Reynolds number. So we have a very controlled system. So the fluid elements, the layers of fluid will move in a very predictable way. They will flow very smoothly and streamlined. So once that we talk about this, I also want to mention that we will assume constant physical properties. That means that the viscosity and the density are going to be constant always. There is going to be some gravitational effects on the flow. So the gravitational forces are going to be only important in y direction. So that's why we have only a non-zero component of the vector in y. We will be interested in the steady state solution. That means we are not going to care about what happens in the transient state. We want to find the solution when the system no longer depends on time. And also there is not going to be other external sources of movement. So there might be a case in which we might have a pump. So this pump is a mechanical device that you have in your home that is going to transport water from the bottom to the top, to the roof of your house. So this pump might have a mechanical effect that is going to push the fluid in X direction. So for this case, we will not consider the effect of a pump. So the only source of movement comes from the top plate, which is moving with a velocity uv. So also, since this is a very well studied, a very well controlled system, so we will not have velocity contributions in y direction. So that means that the fluid will not move in y direction. It will not move either in z. So the only important relevant component of the velocity is in x direction. So the fluid only will move in this direction. So then once that we assume these conditions, now let's talk a bit about boundary conditions. So these conditions are going to be important to obtain the velocity field. So at the bottom plate, we have non-slip boundary condition. So that means that ux, when y is equal to 0, is going to be equal to 0, which is what we define here. And then at the top, we have when ux and when y is equal to h, we have that the top plate is moving with a velocity uv. So those are our boundary conditions. Now let's talk about the Navier-Stokes equations. So those are the equations that we are interested in solving. So what information can be obtained from this? The continuity equation expressing Cartesian coordinates is here. So we have a simple sum of partial derivatives. But since we talk that we will only have a non-zero element for the velocity field, which is ux. So these two derivatives are 0 because uy and uc are 0. So that means that this derivative is going to be 0, which means that ux is not going to depend on x. So this implies that ux will only depend in y, because if you remember that I said that the velocity values of the top layers of fluid, the velocity values of the layers of fluid that are at the top are going to be higher compared to the layers of fluid that are close to the bottom. So the fluid will definitely depend on y. So that's basically the information we can gather from here. And it will obviously not depend on c, because nothing is happening in c direction. There is no external source that is causing that the fluid will move in c direction. So that's why c is called the neutral direction, because nothing matters in that direction. So now the most interesting thing, we will talk about these momentum conservation equations, which are very complex. So we have this very complex system of equations. So I already wrote all the terms of these equations. So remember, momentum conservation, it's a system of three partial differential equations. So we have the Navier-Stokes equation in x direction, the component x, we have the component y, and we have the component z. So with these assumptions, with these points to consider that we already talked about, let's simplify the system of equations. So this is why it's important to understand the physics behind this flow, because it will allow us to simplify the momentum conservation equations. So you remember I said a steady state, so we will not care about the temporal term. So this term is going to be 0. Oh, this is t. I apologize. So you remember for this term, ux is actually different than 0 because the velocity field is going to take this form. But from the Navier-Stokes equations, from the continuity equation, we saw that this derivative is 0. So this term is going to be 0. So ux is going to depend on y, as we discussed before, but uy is 0. So this term is equal to 0. So ux is not going to depend on c, and also uc is 0. So this whole term is 0. So this is the pressure gradient. So you remember I said that there is no external sources of movement. So that means that we will not have a contribution from a pump. So the pressure gradient in x direction is going to be 0. So similarly, the first derivative of ux with respect to x is 0. So that means that the second derivative is going to be also 0. So ux is going to depend on y, so this is non-zero, and ux doesn't depend on c, so this is 0. And the gravitational term, so this is actually you remember we define our gravitational field. So in x direction, we will not have a contribution from the gravitational forces, so this is 0. So in conclusion, this whole equation is simplified to only this. So we will save this equation for later. And now for the component y. So this is really easy. So you remember again, our velocity field is going to be adopt this form. So uy is going to be so this is t. So we do not care about the temporal term. So this is 0. So ux is different than 0, but uy is 0. So this is 0. All this term is 0 because uy is 0, and uy and uc are 0. So this is the pressure gradient in y direction. We don't exactly know its value, but it's non-zero. I will show it. I will show it to you why. So uy is 0. All these terms are 0 because uy are 0. And you remember the gravitational vector. We have something like this. So the equation in component y is actually going to take this form. So 0 is equal to the pressure gradient plus this. And well, this is actually like this. So this equation is actually a very famous equation. It's called the hydrostatic equation. So if the gravitational effects are mattering, are important in y direction, so there is another force, another. Remember that Navier-Stokes equations are a balance of forces. So here we have the gravitational forces have to balance the pressure, the effect of the pressure on y direction. So this equation is equal to 0. So these two have to balance each other. So this is the equation of the hydrostatic. In fluids also the pressure depends on the height, of the channel. And then we have the component C. So this is even easier to obtain, to simplify. So this is temporal term. So u c is equal to 0. So all these derivatives are 0 because uc is 0, uc and uy are 0, uc all this is 0. We don't exactly know the value of this term. uc are 0, and then we don't have a contribution of the gravity in c direction, so this is 0. So the equation is simplified to this. 0 is equal to minus. So in summary, what are our equations? So in x direction, we have, you remember we have this equation. So I'm going to copy it. In y, we have this equation. And in t, we have just this equation. I'm going to write it straight here. So you can notice that we only have a velocity, an equation for the velocity in x direction, which is this one. So that means that this system of equations is not coupled. So that means that we do not need to solve this equation simultaneously. So this equation, the one at C, just tells us that the pressure is not going to depend on C because the partial, the derivative of the pressure in C direction is equal to 0. We have the equation of hydrostatic, which balances the gravitational effects with the pressure term in y direction. So we do not need to find P in order to find ux. So we only need to solve this differential equation, which is actually is no longer partial. So we have something like this. We have an ordinary derivative, which can be easily solved. So this is what we are going to do. So the viscosity can go through the other side. So that means that the viscosity will not contribute to the velocity values. So let's solve this equation. So you will agree with me that this equation can be expressed as this. So if the derivative or something is equal to 0, that means that this something has to be equal to a constant. So this constant is going to be, we are going to call it C1. And then we can solve this, we can separate the derivatives. And then we will integrate in both sides. So this will give us this simple equation. So we have two constants in order to find the velocity field in x direction. So you remember from our boundary conditions, which are here. So at the bottom plate, so let me rewrite these boundary conditions here. When ux is equal to ux at the bottom is going to be 0. So the boundary conditions, and ux at the top is ub. So since this equation is second order, so that means we need two constants. So we already have two boundary conditions, so we can estimate this C1 and C2. So when y is equal to 0, this is ux is equal to 0. So that means that C1 multiplied by 0, which is this equation, plus C2. So 0 is equal to C2. So C2 is 0. So we already found the first boundary condition. Now when y is equal to h, ux is equal to ub, which is equal to C1 multiplied by h. So C1 is equal to b divided by h. So that means that our velocity field is equal to bh multiplied by y. So we substitute C1 and C2 here. So this is our velocity field. This is what we were looking for. So that means that the velocity profile is going to be linear. So that's why I already spoiled before here the solution. So we will have a linear velocity distribution. So the closer we are to the bottom, the lower values of the velocity we will have. And obviously we are at the top, ux is equal to ub. So let me rewrite this equation like this. So ux over ub. So I'm just passing ub to the left side. So now we have a dimensionless equation. So y over h is going to be within the domain 0, 1, and ux divided over b is going to be within the domain 0, 1. So if we plot this equation, we will have something like this. So 0 to 1. So this is y over h, and also 0 to 1 ux over ub. So the velocity profile is just simply something like that. So we have a 40 degrees angle. So this is the solution to the simple shear flow. So the velocity field is going to be linear. Now let me quickly just calculate something very interesting, which is the average, which is just defined as this in bracket. So the average velocity is estimated as the double integral of the velocity field we just calculated over a characteristic area. So, as I said before, the 3D channel representation can look something like this. So here we have the height of the channel. We have some white W. So here all this surface is moving with a velocity UV, and all this surface UX is equal to 0. So now let's calculate this integral. So this integral goes from the first integral, which is going to be for the y direction. So it goes from 0 to h, and in c it goes from 0 to w, and the same here. So the integral, this one, is just simply the product WH. And this is an area, which is this area here. And now the derivative at the top, which is so ux, remember, is b over h multiplied by y. So we need to integrate that this equation. So the velocity field does not depend on c. So we already have the first integral. And now we just need to integrate this equation, which is just simply, remember the integral, all of this is constant, so b over h. So you remember you're simply calculus, integral calculus. So this integral is just simply going to be simplified as and then we need to apply the integral limit, and you will see that you will end up with something like this, which can be simplified further. So the average velocity is just this equation. So you can see this equation does not depend on y. So this is just a constant. So why is it important to estimate the average velocity? So from our solution of equations, we found that the velocity profile is linear for simple-shear-flow. So it's going to take this form. But the average is just a constant. So it's just a value. So this is, and this red line, let me draw it like, so this is just the average velocity, which is just a constant. So the average velocity tells us an idea of a representative value of the velocity in all the layers of the channel. So in fluid mechanics, sometimes it is not possible to find an analytical solution for the velocity field for the geometry we are interested in. In this case, for simple-shear-flow, it was possible to estimate this analytical solution, which is this one. But sometimes we might have very complex geometries, and it's almost impossible to find an analytical solution for the velocity profile. So that's why we need to apply numerical methods. But also, sometimes it is possible to estimate the average velocity for this flow. So we will not obtain an accurate value of velocity, but this will give us an idea. This average velocity will give us an idea of how the fluid will move and what is the representative value of the system, which is this value we just estimated. And just to conclude, you remember that I say that the diffusive flux of momentum can be estimated as this. And we already estimate ux, and the gradient of ux is just b over h. So let me rewrite this equation as this. So the viscosity is just going to be b over, can be estimated as follows. So why is this equation so important? So this simple shear flow is used a lot in different fields of physics because it will allow us to obtain a value of the viscosity of the fluid. So there are some special machines that are used in the laboratory, which are called rheometers. So in simple shear flow, so these machines, these rheometers reproduce simple shear flow. So we have a fluid between two parallel plates. As you know, the top plate is moving with a velocity uv, the bottom plate is fixed. So the machine is going to apply a force over the top plate. So the machine knows which force, the value of this force that is being applied in order to make the top plate moving with a velocity uv. So you know this value from the machine, from the rheometer, and you also know at which value of the velocity the top plate is moving, because you will fix that in your experiment, and then you know the distance between the parallel plates. So you know all this information, which will be useful to estimate the values of viscosity. So this is why simple shear flow is important in the laboratory, also to study complex fluids. So I just wanted to mention some applications of this flow. So with this, I conclude this video. So in the next video, I will be solving a similar problem, but now we will have a contribution from a pump. So that means that now we will have a component different than zero for the pressure gradient. So these equations, the solutions that we obtain here are going to be important for the next videos, where I will be introducing the numerical methods that are used to solve the governing equations. So thank you everyone for watching this video. Let me know if you have any questions or suggestions in the comments.